The cross-sectional dimensions of a beam this time is a I section and is a symmetrical I section. The top and bottom planes are having a length equal to 240 mm and the depth is equal to 30 mm, and we have a wave here. Width is equal to 9 mm and the height of the wave is 350 minus 30 minus 30, that is 350 minus 60 is equal to 290 mm. Now the I section is a symmetrical here, so we can very well mark the centroid just by observation, and he has given the location of point A, which is 90 mm below the center of gravity, and one point is shown which is at the bottom of the bottom flange. Iz is known this time, and the bending stress at the point A is known to be 35 megapascal tension. So at this point we have tension stress is equal to 35 megapascal, and state whether the normal stress at B is a tension or compression. Now once we have a stress below the neutral axis is a tension, so stress at B is also tension. In the second part, the allowable bending stress, that is the maximum value of a bending stress, is 165 megapascal. Determine the magnitude of the maximum bending moment M that can be supported by the beam. The stress at A is given to us is a positive value and is equal to 35 megapascal is tension. Stress at B we have to find out, and maximum value of a stress is sigma max is given as 165 megapascal, and we have to calculate the value of M. And the value of Iz is also given, that is 402.24 10 to the power 6. So one you have to calculate the stress at B, and second you have to calculate the value of M. The bending stress sigma B, which one is a function of Y, is given as minus M by Iz multiplied by Y. This time the bending moment and Iz is constant. It means that we have a ratio of the bending stress at A and the bending stress of B is same as the distance YA and the distance YB. So the point A here is below the center of gravity, and here we are going to set our Z axis, which one is the horizontal axis, and Y axis is vertical. From the bottom here, the centroid will lie at exactly equal to 350 by 2. So in this case we have Y bar will be same as equal to 350 divided by 2, that is equal to 175 mm. This value represents YB and this value represents YA, but you have to take the value of YA as a negative. So in this case we have YA is equal to minus 90 and the distance YB will be equal to same as the distance of Y bar is minus 175. So in this case the value of M by Iz is a constant value, and therefore we can say that the bending stress at point A divided by the bending stress at point B will be same as the distance of YA, that is the point A from center of gravity, divided by distance YB, the distance of point B from center of gravity. Value of sigma A is a positive value, so we have 35 megapascal divided by sigma B. Both time it's a negative will be get cancelled. Sigma A is equal to 90 divided by 175. Both are negative will cancel. So we have a bending stress sigma B will be equal to 175 multiplied by 35 divided by 90, and it come out to be positive value. It means that it's a tensile. You will get this value close to 68.1 megapascal. In the second part he says that the allowable bending stress equal to 165 megapascal. So for present case we are getting the maximum bending stress equal to 68, but he says that the load is increased and the bending stress come out to be maximum equal to 160. Then what is the corresponding value of M, you have to find out. It is known here that the maximum bending stress will be occur on the top fiber and the bottom fiber, and from center of gravity both the top and bottom fiber are equidistant. So the value of C for the top fiber and the bottom fiber is same. So in this case the value of C will be exactly equal to 350 by 2. So the value of C will be equal to 350 divided by 2. M upon I is equal to sigma B maximum by C. In that case, we can calculate the maximum bending moment M equal to maximum bending stress is given as 165 megapascal. I is given as 402.24 into 10 to the power 6, and whole thing is divided by C, the maximum distance out of top and bottom fiber from center of gravity. This time we have C is equal to 175. So you have to divide it by 175. This answer will come in Newton mm. Is 379.25 into 10 to the power 6 is Newton mm. Is same as equal to 379.25 will be kilo Newton meter. A simply supported wide flange beam, that is W beam here, which one is also called as I section beam, and this section is symmetrical I section. And the cross-sectional dimensions are as shown in figure. We have top flange and bottom flange. The width of the flange equal to 200, depth equal to 25, and we have one central web whose width is equal to 25 and the height is equal to 250 mm. The maximum tensile stress on the cross section at C, exactly at C, we want to find out what is the bending stress. For this one, we should know what is the distance of the top fiber and the bottom fiber from the centroidal axis. So by symmetry here, vertical axis represents here the axis of symmetry, and exactly the halfway of 250 plus 25 plus 25, that is 300, divided by 2. We have centroid. So this one is the position of a centroid, and the position of the centroid, that is y bar, from the bottom fiber of the bottom flange will be equal to 150, that is 250 plus 25 is 300, 300 by 2, that equal to 150. The centroid AG is at a distance equal to y bar, that equal to 150 mm. In addition to this, we have to calculate here the moment of inertia of this symmetrical figure. We have to also calculate the bending moment at point C. So what we'll do first, we'll calculate the bending moment here first, and we are keep ready with the bending moment. Once we know the bending moment at C, then we'll find out here the moment of inertia of the given symmetrical I section above the centroidal axis. So first of all, we are interested to know what is the bending moment at point C. For this one, we require the reaction AY and the reaction EY. So since we are interested in AY, we'll take the sum of the moment about E must equal to 0. So to find the value of AY, we'll take the sum of moment of all forces about the point E, and we'll take the clockwise moment as a positive value. So AY will make a clockwise moment, and the total distance is 1 plus 2 plus 3 plus 2 is 5. So in this case, the clockwise is positive, so we have AY into 5. 20 kilonewton, that is acting at point B, will make an anti-clockwise moment, that will be negative, and the distance is 1 plus 1 plus 2, that equal to 4. So we have minus 20 into 4. Then 20 kilonewton acting at C will also make an anti-clockwise moment, and the distance equal to 1 plus 2 is equal to 3. Anti-clockwise is negative, force is equal to 20, perpendicular distance equal to 3. And this 20 kilonewton acting at point D will also make an anti-clockwise moment. So we have minus 20, and the perpendicular distance is same as equal to 2, that equal to 0. Only unknown in this equation is AY, so we can find out the value of AY. So we get the reaction AY is equal to 36 kilonewton, and answer is positive. It means that it is acting vertically upward. Now since we are interested at C, so we'll make a cut at point C. So exactly on the left hand side, we'll make a cut. So just on the left hand side of C, we'll make the cut to find out the reaction at point C. So only A, B, C portion we'll consider, but we are on the left hand side, so 20 kilonewton force will not be shown. One reaction you have to show is the vertical reaction equal to AY, and we have value of AY is same as equal to 36 kilonewton. At point B, we have vertically downward force is equal to 20 kilonewton. The distance between A to B is equal to 1 meter. B to C is equal to 1 meter. And here we have, let assume the shear force is acting equal to Vc, and we have reaction is shown is anti-clockwise is equal to Mc. So here we'll take the moment of all the forces above point C. So we have sum of moment of all forces above C must equal to 0, and here we'll change our sign convention. Instead of taking the clockwise positive, this time I will take the anti-clockwise positive. In that case, this value of MC is anti-clockwise is positive. The moment of AY about point C is a clockwise is negative value. So we have minus AY into the distance equal to 2. Then the 20 kilonewton above C will make an anti-clockwise moment, that will be positive value because it's a anti-clockwise. We have force is equal to 20 and the distance equal to 1. And here we have assumed the MC value anti-clockwise. Anti-clockwise is positive, so we have plus MC must equal to 0. So in this case we get the moment about C will be equal to AY will be positive on the other side is 36 multiplied by 2 minus 20. That is, we have 72 minus 20 is equal to 52 is kilonewton meter. So at point C, we have the moment is shown anti-clockwise, that is the sagging effect, and is taken as a positive value equal to 52 kilonewton meter. Next job is to calculate the value of moment of inertia of the given I section. So this figure is consist of one standard rectangle of total height equal to 250 plus 25, 275 plus 25 is 300, and width equal to 200. So this given figure is consist of this largest possible rectangle whose width is equal to B1 is equal to 200 mm, and the H1 is equal to 250 plus 25 plus 25, that equal to 300. From this entire rectangle you have to subtract this rectangle. Now check what is this rectangle. This is 200 minus 15, that is 185. 185 divided by 2. So this rectangle you have to subtract from the given figure. So let's check the width of this rectangle. The width of this rectangle is basically 100 and this is 7.5. So this width B2 will be equal to half of this. Half of is 100 and half of 15, that is 7.5. So it is equal to 92.5, and the height is same as equal to H2, that equal to 250. So this is minus value. Almost similar rectangle you will get here also. So this will be equal to 2 times. So this is the centroid of figure number 1, and here this is the centroid of figure 2, that is C2. For both the C1 and C2, we have Y1 value is same as equal to Y2 value will be equal to 0, and is same as equal to Y bar. Y bar on this axis will be equal to 0, and from bottom it is equal to 150. Suppose this one is our Z axis and Y axis. In that case, Y2 value, Y1 value and Y bar will be equal to 0 with reference to this Z axis. So the moment of inertia of this figure will be equal to Iz, and here we'll use the parallel axis theorem. Moment of inertia of the first figure Iz1 plus we have area A1 multiplied by the perpendicular distance, that equal to Y1 minus Y bar, and we have square of it. Now this is a minus sign, so you have to continue with minus sign. Moment of inertia of the second figure, that equal to Iz2 plus we have A2 into Y bar minus Y2 whole square, and this area repeated 2 times. Now here Y1 and Y bar, they are the same value, so this term will cancel out, and Y bar and Y2 is also same term, so that will also get cancel out. It means that you are getting this answer is same as equal to Iz1 minus 2 times of Iz2. Now 2 times of Iz2 means that if we consider this rectangle and this total rectangle, that will be equal to 2 times of Iz2. So IZ1 basically here a rectangle of dimension, that is the original dimension equal to 200 and height is equal to 300. And the height of this rectangle except the web will be equal to, I will show the height first. Height will be same as equal to 250. And the base you have to subtract 200 and 15. So basically we have joined here this rectangle which is shown as this rectangle as well as this rectangle. So this one is a quick calculation method here. You take the outer rectangle in a symmetrical I section. Outer rectangle will be equal to 200 is the width and the height will be equal to 250 plus 50, that equal to 300. These two rectangles as per the proof here will be equal to, height is equal to 250 and as far as the width is considered, width will be equal to 200 minus 15. 200 minus 15 will be same as equal to 185. 185 is same as 92.5 into 2 is 185. So we can very well calculate here the moment of inertia Iz. It's a simple BD cube, that is B1 D1 cube, and we'll call this as B2 and D2 cube. So in this case we have 200 multiplied by 300 cube minus 185 is the base and the depth is 250 and we have cube of it and we have divided by 12. So what is this answer will come will be the Iz value. So from this you will get the value of Iz for the I section. This answer is come out to be 209.11 into 10 to the power 6 mm to the power 4. Next time remember, whenever you have to calculate the moment of inertia Iz of a symmetrical I section, you just take the outer rectangle and find out the value of Iz1 and subtract the value of the total rectangle formed by these two value of rectangle whose height will be equal to 250. So this height is also equal to 250 and the width of this one is same as 200 minus 15, that will be equal to 185. So very quickly we can calculate here the Iz value. So we know the value of Iz equal to 209.11 10 to the power 6. Bending moment about the C come out to be 52 kilonewton meter. Now once we ready with the bending moment at point C and the Iz, we are able to calculate the maximum tensile stress on the cross section at C. Remember the value of bending moment at C was positive. So the maximum bending stress is at the top fiber and bottom fiber. Let's say here we have a point A on the top fiber and this distance of top fiber, that is Y, will be same as equal to 150. Because of symmetrical section, the bottom fiber and the top fiber will be at same distance. So at bottom fiber YB will be negative value of 150 mm. The bending stress at any distance Y is given as sigma B, which one is a function of Y, is minus M into Y divided by I. Now I want here the maximum tensile, so you have to put the value of Y negative. Now in this equation the value of M is positive and we want a positive value for tensile stress, so you have to select the Y as a negative value, that is you have to select the value of YB. So we have maximum value of a bending stress, sigma B maximum will be tensile in nature, is minus M into YB divided by Iz. So we have minus M value is same as 52 kilonewton meter, is 52 into 10 to the power 6 Newton mm. YB value you have to use as minus 150. So we have minus 150 minus minus become plus and divided by Iz, which is equal to 209.11 into 10 to the power 6. Solve this, you will get a bending stress in megapascal and it is guaranteed is positive value, that is a tensile, is 37.3, that will be megapascal. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.